I am not explaining, you already know about heat pipe. The heat pipe has got its container, the big structure. You have an evaporator section, you have an adiabatic section, you have a condenser section. You apply heat here, you remove heat on the other side. Or rather, the heat pipe is used to transfer heat over a long distance with minimal temperature drop. This is the idea. So this also means that the heat pipe surface, when it operates as a heat pipe, is more or less isothermal. So it has twofold advantages. One is that you can transfer considerable amount of heat. Another thing is that you can produce an isothermal surface. The second one is called the heat spreader application of a heat pipe. Or rather, when the heat pipe operates, there is not much of temperature gradients produced on the surface. So when I have applications like electronics cooling, for example, I would always like to have a constant temperature surface as far as possible. So heat sinks which are designed using heat pipes is a very attractive option for that. We have the cylindrical design and the flat design, which we have been talking about. Then we have the three sections: adiabatic, evaporator, adiabatic and condenser section. Also we have the regions like the wall region, the wick region, and the vapor core. I'm not going to explain further about it. This is a conventional design, and then this is the zoomed up picture of what is happening inside the heat pipe, the evaporation taking place, the condensation taking place, etc. And the wick structure inside, the wick structure we have been talking about. So please remember, in a conventional heat pipe, the vapor form is confined inside the vapor core. The liquid is confined inside the wick structure. So you have definite regions in the heat pipe where you can find the vapor and where you can find the liquid, and the circulation is set up because of capillary effect, which is produced by the wick structure. So this is the functioning of the heat pipe, and it does not require any external energy. Just grabs a little bit of energy from what you supply, what you actually transfer, in the form of a capillary action, and then so we call it a passive device. We don't have any active components in the heat pipe. So that is the good old design of the heat pipe, and this is the working principle. You already know about all these things. I don't want to explain it further. Now, what is a micro heat pipe? It's a simple thing. I said that I don't have the wick structure. I don't have the wick structure. Then how is the wicking produced? Or how is the capillary action produced? It's so simple to understand. Suppose I have a channel like this, just a triangular channel, or rather any channel with a polygonal cross section, where I abide by certain rules when I have the geometry of the channel, so that these corners produce a capillary action. So this one unit I have shown here is a heat pipe. Can operate as a heat pipe. If it is properly designed, I can have an evaporator section, a condenser section. I can have an adiabatic section also if I want inside. I supply heat here. So before that, just like the charging procedure of the heat pipe, I charge this heat pipe, evacuate it first, put a little bit of working fluid inside under vacuum so that it evaporates, and so on further heating it. Initially it is in the saturation condition. On further heating, more liquid evaporates and becomes vapor, and the vapor moves through the inner region, and the corners provide the wicking action for the liquid to come back. So I don't have any extra wick for this. The corners of these channels themselves act as the wicking, and the central region of these channels act as the vapor. So, as I was telling, what makes this happen is the size itself. Only if it is small this works, okay, and this angle should be appropriate, so that there is sufficient capillary action that is produced by the corners. So now when you do that, when the circulation happens inside, what happens inside is this. You have the vapor inside, you have the liquid meniscus formed. Beyond the liquid meniscus, you have at the corners the liquid is moving. So it is separated from the vapor by the liquid meniscus. So I don't have a big structure, but the liquid is confined to the region on one side of the liquid meniscus and the vapor on the other region. But there is a difference between the wick, the heat pipe, that the area of cross section varies along the heat pipe. Okay, so the area of cross section, if I cut cross sectional areas, this is what you are going to see when you move from the evaporator section to the condenser section. When you look at the condenser section, the liquid region will be quite large and the vapor core will be small. It takes almost a cylindrical shape. So it moves from a triangle to a cylindrical shape. when you cut across.